video is about how we would solve systems of linear inequalities. We're very used to solving systems of equalities, and oftentimes our solution might be a point or a couple points. In this case, we're going to see that the solution to the system of linear inequalities is actually a set of infinitely many points. And so let's see how we would go about doing that. Our system on the left is made up of 4 inequalities. The first thing we would like to do is graph the boundary lines of our region that's going to be the solution to our inequalities. When we're graphing a boundary, I kind of pretend that that inequality symbol is an equal sign. So for that first one, I'm going to think of x is greater than, instead of x is greater than, I'm going to think of x is equal to -3. And that's just a vertical line. I'm creating a dotted line and not a solid line because x equals -3 is not part of our solution. It's just x is greater than -3. What that means is we would like to know all the points, all the ordered pairs whose x-coordinate is bigger than -3. So I'm about to shade all of ordered pairs for which that holds. Everything to the right has an ordered pair where the x-coordinate is greater than -3. And because our boundary was dotted, any point that lies on that boundary line is not part of that region. Let's do the next line. 2x plus y is less than or equal to 10. To graph the boundary line, I'm going to think of 2x plus y equals 10. Our x-intercept is 5, and our y-intercept would be 10. So you can also figure out that the slope here is going to be -2 if you would like to graph in some more points on your line. I'm going to connect these points with a solid line because our boundary line is part of our solution region. 2x plus y is less than or equal to 10. So that line does count here. Now, which side of the line would I shade? Would I shade above the line or would I shade below the line? The way I like to find out the answer to this question is to test a point. So let's say that we are testing the point 0, 0. 2 times 0 plus 0 is less than or equal to 10. Does that point satisfy our inequality? 0 is less than or equal to 10. Yes, it does. So since 0 is less than or equal to 10, 0, 0 is a solution, and it should be shaded. So I'm going to shade everything below this line. You can start to notice that our solution set is going to be the points that satisfy all 4 of these inequalities at the same time. So I'm interested in the overlapping shaded regions. So you can see right now the pink and the blue are the overlapping regions. So I'm not going to shade anything to the left or continuing to the left of our line. I'm stopping at that dotted line because I know that anything to the left isn't going to be part of our system of inequalities. Let's graph that third boundary line. And our third line is y is less than or equal to 4. So our boundary line is y equals 4. That's a horizontal line at 4. It's solid because it's less than or equal to 4. I'm interested in all points whose y-coordinate is less than or equal to 4. So that means I'm going to shade all points underneath that line. And again, I'm interested in where our shaded regions are overlapping. So you can see, instead of shading everything under that line, I'm just starting to shade the region that I know is going to be part of our solution. I only have one more region to graph, and then we can see where all 4 regions overlap. Y is greater than 1/2 x minus 3. I know that that line has a y-intercept of -3 and a slope of 1/2. So I'm going to plot some points on that line. Am I going to connect this one with a solid or a dotted line? That's right, I'm going to connect it with a dotted line because our boundary line for this region is not included. Its y is greater than, not greater than or equal to. Should I shade above the line or below the line? Let's test a point. Let's test 0, 0. Is 0 greater than 1/2 times 0 minus 3? 0 is greater than -3. That was true, so I'm going to shade where 0, 0 lies. I'm going to shade above this line. And again, now I can really see this beautiful region of overlapping colors, and that is our final solution region. How many points exist in that region? Infinitely many. So the reason that we solve these systems of linear inequalities by graphing and not just by using algebra is because now we can really see our solution region, and I don't have to describe infinitely many points trying to use words or symbols. So this picture really represents the solution. You might hear this region be called the feasible region. Feasible meaning it's the region that works. It's the region where all your solutions lie. Now let's see if we can figure out exactly what points are really in this feasible region. I have 3 questions here. Is the point 1, 1 a solution? In order for it to be the case, we would have to make sure that x equals 1 and y equals 1 satisfy all 4 inequalities at the same time. So I can go through and I can plug in x equals 1, y equals 1, one at a time into our 4 inequalities and make sure that each one works. But I'd rather just take a look at my feasible region. The point 1, 1 is right about there. That is very clearly in the feasible region. It's in our solution region. So yes, 1, 1 is a solution. And if you would like, you can go through all 4 inequalities, plug in, and verify that that is true. How about the point -3, 0? That point is right here. It seems to be right on the edge of our solution region. However, it lies on a dotted boundary line, so it is not part of our solution region. You can verify this by investigating the very first linear inequality. X is greater than -3. Our x in our point, -3, 0 is -3. Is -3 greater than -3? No. -3 is equal to -3, but not greater than it. So that's a verification of why the answer is no. Now, how about the point -3, 4? That one's right here. It lies on 2 boundary lines, one dotted, one solid. The answer to this question is still no, for the same reason as above. If you plug in -3 as your x coordinate to that very first inequality, we get the same problem. -3 is greater than -3, and that is not true. You might argue that it works for our green boundary line, y is less than or equal to 4, but in order to be a solution in our solution set, that point has to satisfy every single linear inequality simultaneously. So it's not allowed to work for one and not work for another one. As soon as it doesn't work for one inequality, that point is not a solution. Good luck!